Good afternoon, YouTube peoples. All right, today I'm gonna teach you about trees. Woo! I'm excited about this one. This one really took me, really grabbed onto my curiosity today. And I can't remember what I was doing when I thought about this question. Oh, I was taking a walk. I was taking a walk on the road during my lunch period, and I saw this really tall oak tree, even taller than this one, but you can just tell how freaking far the branch goes. And if you follow the branch all the way out, I'm taking full steps right now, all the way out. Goes and goes and goes and goes and goes. And then eventually, at the very end of the tree, you get to little leaves. And I just thought, how on earth could Jessica, that leaf, and Bonnie, that leaf, and Brian, that leaf, and all the other leaves, how could each individual one, and then all the individual leaves of this tree, receive the nutrients that they need, being so far away from the trunk? It had to travel all the way up, all the way down, all the way up, all the way around, onto there. And so I did a little bit of research, and what I started to realize from Scientific American, thank you very much for the nice publishing, Scientific American, is we need to start with a concept of water, H2O. And if we think about H2O, H2O is a really curious molecule because it has, I'm gonna see if I can do this with my fingers. It has an oxygen molecule, it has a hydrogen molecule, and then it has another oxygen molecule. And it's kind of in a triangular shape, like this. And interestingly, these oxygens really want the electrons. They want them all to themselves. And this lonely hydrogen out here says, okay, fine, you can have them some of the time, but I'm still gonna keep my hand on them. But you can have them a little closer to you. And so these oxygen molecules, this one and this one, they create an electric or a negative charge, and the hydrogen becomes a little positive up here because it's not holding so closely onto the electrons on average. So you have a positive charge and you have negative charges over here. And as you can imagine, now you have a molecule that has charges, and if it finds another water molecule, then they're gonna attract one another, because what attracts to something else? Well, or what attracts to a positive part of a molecule? A negative molecule, or a negative part of another molecule. So every positive part finds a negative part of another molecule, and they start sticking together, and that's how you get water droplets that stick together. For example, these. Maybe these are a better example. But theoretically, you know, these water molecules, you see how they've pooled up? It's because they're sticking together. They could just be flat, completely smeared across without holding on to one another, but that's not how they interact. They make little balls, little puddles, little droplets, because they're sticking to one another, because each water molecule has a positive and 2 negative parts to it, and it sticks to all the others. So that is exactly the major force that is used to get water from here all the way up, all the way up, all the way up, even as high as 300 feet, 100 meters for the highest redwoods or Amazonian trees. You might be asking, okay, how the heck does that happen? How could a tree suck all that water up itself, considering I can barely even suck Sprite out of a glass with a straw? So let's talk a little bit more. A tree, as it's growing, will create, and let me use this plant over here as an example. When this tree is younger, what it does is it creates what's known as xylem. It's all in the tree, and xylem is made out of cells that grow very long and really, really, really little wide. They're very, very, very small in diameter. So small, in fact, that in about a centimeter, assuming that my finger is more of an inch, maybe in the span of a centimeter, you can fit about let me think here. You could fit about, in some of the really big trees, you could fit about 10 cells. No, wait. Oh yeah, I got 2 different numbers. Depending on the tree, you could fit in a centimeter wide stalk. Oh, this is a good example. This is a papaya. So if you go across this stem from side to side, there might be 10 cells. There might even be 100 cells. There might even be 200 cells. There could be up to, the number I had was 3 to 5 microns per across. So really you could have, well, the math there would be 1 centimeter is 10,000 microns. So if you divide 1 centimeter by, or 10,000 microns by like 5 microns, then you're looking at 5 or 2,000. You could have 2,000 xylem cells from across from one side to the other, which is insanity. So it really depends on the plant and also the stage of life. But that's all to say that they're very thin side to side. So you can imagine they're very thin straws, because each little cell grows really long, up to about half a centimeter long. And then, like we just said, sometimes you could fit 2,000 of them sideways. So there's like boom, boom, boom. There's boom, 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 boom. 2,000 or 500 or 100 of these cells packed in sideways, all going really long up the stalk, really about half a centimeter each. And that makes up the xylem. So what's really cool about that is you have a bunch of tiny little straws that are all packed in. This is a good visual, but they're even thinner, because obviously you could fit like the number I quoted, 100 of them across even a centimeter wide, for example. And each one carries water up it through a couple of different means. One of the means, there's 3 forces. The first force is capillary action. Capillary action means that Water tends to stick to the sides of a straw, for example, and climb up it, because I believe it's the forces we talked about earlier, but I also believe it might have to do more with gosh, actually I can't remember why water sticks to the side of things. I'm not sure if it's because of the charge anymore for that, but the tendency for it to stick to the walls of a straw and then climb up it, that is called capillary action. And then that's the first force. The second force is a force of a pushing force from the roots. And the reason you get that force is because if you think about the soil, how much water is in the soil? There's really a lot of water in the soil compared to the tree, right? And the very wet soil has a much higher concentration of water than the tree's roots. So if you think about a waterfall, the waterfall is going to go from a high place to a low place, right? It's going to fall down the waterfall. So if you have high water content here in the soil, the gradient of high water concentration is going to flow into and push into the tree and the tree's roots by falling down into the low concentration of water in the tree's roots. That's called an osmotic gradient. That's a pushing force, and we call that root pressure. So the combination of root pressure with capillary action is the first force, root pressure is the second force. Together, those forces can supply water up a tree up to about 6 feet to 9 feet, about 2 meters to 3 meters tall of a tree. So once you already get to this size of a tree where these leaves need water, you're looking at adding a third force. And that third force is called evapotranspiration. Can you say that? Very good. Evapotranspiration is the process of the sun during the day blasting these leaves with heat. They open up their little stomata, or their little holes, and they let water out. In doing so, these little cells are going to lose water, and that is going to mean that the cells next to them are going to have more water. We're going to imagine that there's a lot of water in here and there's a lot of water in these leaves. So as the leaves evaporate their water, the water in here is going to be pulled into the leaves. And why would it be pulled? Well, if you think about what we said before, you're going to have the waterfall going from high concentration of water to low concentration of water just through a gradient. You're also going to have the capillary action of less water here and high water here, pushing the water up. But really what happens is you create a vacuum up originating here, because as the water leaves, that creates a vacuum that pulls the water from down here. But why does it create a vacuum? I'm wondering why. I want to say it's because of the fact that water is both positive and negative, and because water is both positive and negative. Or it could be more of a thing of the cells themselves. Oh man. Oh boy, this might be a question for next time. It feels to me like capillary action. But the article I read said capillary action doesn't get it more than 6 feet to 9 feet. So guys, this one's gonna have to end on a note of not understanding the difference between capillary action, which is the going up the straw, force versus creating a suction. I suppose what I could imagine is, okay, maybe that's it. That's it. A tree is a closed system, right? Yeah, it's a closed system of cells, and you can't just like pump air through it willy-nilly or water through it willy-nilly. Like it's there's stuff everywhere in it, and so if you tried to pump something in, like you're gonna push something out, or if you tried to pull something out from this side, you're also gonna pull something in from this side. So as all of these leaves give off their water, that leaves a hole or a vacuum that is pulling the water behind it with it. That's exactly it. It's pulling the water out with it. And a good analogy for that is, you want to imagine imagine a group of kids going to the museum, and their teacher tells them they have to hold hands. If one student decides to just sprint off while still holding the hand of another student, the whole line of students are gonna get pulled by that kid. And so in the same way, all these water molecules are holding hands through the negative and positive sides we talked about. And so when one kid or one water molecule decides to just sprint off and evaporate, that pulls behind, it's still holding onto the hand of the water behind it, and so it's pulling. It's a suction force. And that's my claim. That's what I understand. All right. Wow, 17 minutes. That's crazy. Thank you guys for tuning in. I hope you learned something today. This has been a discussion of capillary action, root pressure, evapotranspiration force, 10,000 microns per centimeter. What else? That's really the gist of it. So, oh yeah, water's polarity in having both a positive and negative sides. And that's what we've learned today. Thank you all very much for tuning in. I hope you guys have a good day. And this has been an I Wonder video. Thanks, guys. See ya.